All right, so let's look at this example over here. So we have vector A that we're given to have a magnitude of 40 meters and points in a direction of 20 degrees below the x-axis. And a second vector is B, which has a magnitude of 75 meters and points in a direction 50 degrees above the positive x-axis. Part A asking us to sketch vectors A and B, and what would the sum of A and B equals to, which is, let's call that vector C this time. So we're going to graphically, represent A, B, and sum of A plus B. All right, so we start with doing the coordinate system, x-axis, y-axis, and I'm going to have the vector A, let's say with the blue color here. So you can see, right? Well, maybe something like this, because this is 20 degrees. So this is vector A. Vector B, 75, which if this is 40, this is roughly double that length. So maybe something like this. So then this is vector B. Then another way I can graphically add those two together and find the resultant, this is known as not a tip to tail, this is a parallelogram method. This is a different one. Parallelogram. For this one, what we do here is we connect those A and B vectors at their tails, not tip and tail, but both of them at their tails, and then generate a parallelogram, which is kind of like projection of each one, like this. Then the resultant vector will be the one that diagonally where their tails are, like this. And this is, let's call this vector C. All right, that's the resultant, A plus B. Remember, vector C is equivalent to the sum of A plus B. All right, so now our goal is for part B is to use the component method of vector addition and find the magnitude and direction of vector C. Remember, if I try to do this, right, 40 meters plus 75 meters equals, I don't know, like 115 meters, well, this would be completely wrong, right? Don't ever try to do that, because even though we're given the magnitude of vector A and B, well, those are two-dimensional vectors, and vectors are not just algebraically added like this. Remember, only when you are working with vectors that both have, basically same components. That means if two vectors are parallel, that means both horizontal or both vertical, then we can add them together, but not when they are like two-dimensional like this. That means what we need to do here is approach this like I mentioned earlier, right, in terms of like this three-step, like let's say approach to solve a problem like this. Step one would be to do this diagram. So then you can see more or less what you're getting. So this diagram, in a way, tells you a lot of information. It tells you when you look at vector A, it's in fourth quadrant. It should have a positive x, negative y components. When you're looking at vector B, it's in the first quadrant. It has x and y components, both positive. And then you have vector C, which is the resultant. That means when you at the end calculate the components of vector C, both should be positive because vector C is also in the first quadrant. And then you should get the direction of magnitude of vector C comparable to what we are drawing over here. See, my drawing here tells me that vector C is actually longer than vector B. And vector B has a magnitude of 75. That means the magnitude of vector C should be, roughly, I imagine, maybe 90. We'll calculate and see what we get, but I'm estimating. See, it's a little bit longer than 75, which is vector B. So I imagine it should be maybe around 90. Also the direction. If this is 50 degrees, well, this is a little bit less. So I imagine it's roughly about half of that, angle. That means my estimation is C approximately 90 meters in terms of its magnitude, and direction is roughly 25 degrees. Those are my estimation, again, by looking at the graph that I have. Now, what I'm going to do here is I'm going to do then the calculations. So for that, I go to step 2, which would be to make the table. So here I have my vectors. This is x components, y components of my vectors. And then I write a vector here, b vector here, and then, so technically what I'm doing is a plus b is equals to vector c. That means the first column is giving me my sum. But because of the type of calculation this is, because of the type of sum, vector addition it is, which is addition of two-dimensional vectors, I have to approach it in a way that first I look at vector A and I break it down into its x and y component. Remember, so here's vector A. So I'm breaking it down into ax and ay components. So that means here I have ax, here I have ay. And ax and ay, according to what we learned, if the direction of the vector given with respect to, let's say, the x-axis, then ax is equals to a cosine theta, ay is equals to a sine of theta. Okay, now that's what I have. But also I have to see that vector A is the fourth quadrant, like we already talked about, and x component positive, but y component negative. So I can put it like that. For B, vector B, if I break them down into components, I'm going to get x component, since again, theta is given with respect to x-axis. That means, see, if I make the triangle for the components, right, this is bx and this is by, I can see that x component is the adjacent, and that goes with the cosine theta. Y component is the opposite, and that goes with the sine of theta. So I write this as bx and by, but because first quadrant, both of them are positive. And what I'm getting here, basically the x component of vector C, if I add those together. And that's my step 2, to make the table. This is known as a vector table, and this is going to be the best way to approach a problem like this. Step 1, diagram. Step 2, the table. Then step 3 will be to find two equations, which is the x component of C, which is basically nothing but using this column over here, where we can see then Cx is nothing but sum of x component, and then Cy is again basically adding whatever we have above that, so right here, which is negative ay plus by. So basically you just happen to be that y component is negative for A. All right, so ax is a cosine theta plus bx is b cosine theta. This is theta A, right? This is also theta B. And here then I have negative sine theta A and plus b sine theta B. Then I can plug in the values. So 40 meters cosine of 20 plus 75 meters cosine of 50 degrees. If I do this, I'm going to get 85.8 meters. If I do this one, which is negative 40 meters sine of 20 plus 75 sine of 50, then I'm going to get 43.8 meters. Okay, so you can see, right? I calculated the components of vector C. Then in a way here, you can say there's also the fourth step, which will be the way of calculating two things. Magnitude of vector C, which will be square root of x component square plus y component square, and those are the values we just calculated. So if I plug in those values, I'm going to get 96.3 meters. And then using the inverse tangent of the y component over x component, if I again plug in those values we just calculated, I'm going to get a 27 degrees, which you can see, right? 96.3 or 27 degrees is very close to the ones that I estimated. So that means you can do the graphical method, estimate the values, and then calculate using the component method, right, or vector addition, and actually get those values, precisely. All right. So let's look at then another example here. So second here. So here's the last example that we have. So we have a vector A points in a positive x direction and has a magnitude of 75 meters. And vector C is equals to A plus B and points in a positive y direction and has a magnitude of 95 meters. Sketch vectors A, B, and C. All right. That means what I have here is this. In this particular example, I'm given vector A in terms of its magnitude and direction, and vector C, which is the resultant. That means in a way, this vector B here is, unknown. It's not given to us. But we know that if I add vector A and vector B together, I'm going to get vector C, which is pointing in a y direction as a magnitude of 95 meters. Right. So first one is to do the graphical, way, y-axis and x-axis. I know one thing, that this vector A is pointing in a positive x direction, right? So this is vector A, and it has a 75 meters magnitude. Vector C, which is the resultant, is pointing in a positive y direction. All right, so let me do that as like this, right? So this is then vector C. Okay, so it's a little bit longer than vector A, so this is vector C. Now, that means the question here is, where should the vector B, so where is the vector B? So when I add A plus B, I'm getting this vector C. Now, remember, it's not very difficult to figure out, because if I use, for example, tip to tail method, I know that the tail of the resultant vector C, remember this one, always starts from point 0, right? Basically the starting point. And then tip of vector A is always connected to point 1, let's say. And then the tip of vector C is always connected to point 2. That means in a way what I have, vector B should be connecting points 1 and 2, just like we had before. That means if I have to do that, vector B will be in that particular direction, right? So this is my vector B, because this is only way then I can have A plus B, tip to tail, right, equals vector C. All right. Obviously, one of the things we do here is we don't keep the vector B over there. So because remember, it's a vector, I can move it because I want to do the calculation. So it's easier to just take this and redraw it right here. As long as I'm keeping the same magnitude, same direction, is the same vector. You can see, right? It's exactly the same vector B. Okay. That means what I have here is more or less, I can figure out from here that with given information, vector B is a vector pointing in a, in the second quadrant. And it's, from what I can tell by just looking at it, right? I can see that vector B is a little bit longer, even vector C. And vector C, remember, has a 95 meter and y hat magnitude, right, and direction. That means my estimation is B to be, I don't know, greater than 100. So maybe roughly 110 meters. Again, I'm just shooting, but, at least, this is some kind of estimation. And then direction is right here. So what is theta B? Well, I don't know. My estimation here is maybe about, 30 degrees from the positive y-axis. So that means 90 plus 30. I'm estimating this to be roughly 120 degrees. Hopefully you guys can see, right? So this is 120 degrees with respect to positive x-axis. I'm estimating that, direction for B. Okay, so that means what I'm doing here is these are my graphical estimation, and I'm gonna do then component method calculation to verify that. All right, so step 2 would be the table. Make this here. These are my vectors, x component and y component. And my vectors are A, B, then adding them together gives me C. So what I have to do here is, remember, so this is where I have the x component of A, y component of A, x component of B, y component of B, and if I add them together, I'm getting the component Cx and Cy. Okay. All right, so one thing I know here is this, that if I look at vector A, well, vector A has no y component because it's just pointing in a x direction. Vector C has no x component because it's pointing in a y direction. And that means that if I calculate, for example, step 3, look at those two equations, which would be ax plus bx equals cx, then what I will get here is this: ax plus bx equals 0 because cx equals 0, which means that x component of A is equal to the negative b component of x component of B. Or you can say, let's say in this case, bx is equal to negative ax. What is ax? Well, since vector A has no y component, that means all of this 75 meters is in the x direction. So that means this is negative 75 meters. All right, so we got the x component of B. Let's look at what we have for equation 2. Remember, our goal here is to find the magnitude and direction of vector B. And I found now x component of vector B. Now I need to find the y component of vector B. And for that, I use the second equation, which is the sum of the vertical components. So this is ay plus by equals cy, but ay is 0, right? Because what I have here is vector A is just horizontal, then plus by, and this is equals to cy. That means the y component of B is equal to the y component of C. And since C did not have any x component, that means this entire vector is in a y direction. That means the y component is equals to 95 meters. That means here we found the y component of vector B. That's all I need. Because in step 4 now, because I have the x and y component of vector B, I can calculate the magnitude of vector B, which will be x component square plus y component square. So I plug in those values, square them, and take the square root, add them together, and I'm going to get 121 meters, which is very close to kind of what I estimated. Second will be to find the direction of B, which will be inverse tangent, like inverse tangent of y component divided by x component. So here I do inverse tangent of 95 meters over negative 75 meters. All right, so what we get here is negative 51 degrees, sorry, 52 degrees. Now, it's important to understand that the reason I'm getting negative 52, because when I'm looking at using the component of vector B, remember, I found the x component is negative 75. That means I found this x component. Okay. So I found this x component, which is Vx equals negative 75 meters. And then I found the y component of the B is 95. That means I found this y component. Okay. And then when I'm using this equation, I'm technically calculating this angle. See this angle for this triangle, because this is the magnitude of B and I'm calculating theta B. And you can see, right, this angle here is 52 degrees, but clockwise from the negative x-axis, right? See, I'm going clockwise from the negative x-axis, and that negative represents that. That means that negative means that you are 52 degrees clockwise from the negative x-axis, and negative, that, you know, indication of the clockwise. Now, generally what I want here is this theta b, which means to do that, we understand that this is 52. From here to there is 180. So then to calculate that, all I have to do here is to find the theta for b. So this will be then 180 minus 52, which will then be 128 degrees. And that's again very close to what I estimated. So that's all I have for the vector b. That means now I kind of reversed engineer, right? So I was given a and c, so I rearranged to find vector b in terms of its magnitude and direction. All right, guys, so that's it for this chapter 1. So make sure to watch it, and then we're going to discuss this in class. And I'm going to give you then, let's say we're going to have more worksheets and things like that on this vectors. So it's important to really be comfortable with vector calculation, because whenever we get to, let's say chapter 2, 3, 4, 5, it's all vector calculation. It's all vector addition. So it's important to get really comfortable, really understand this, you know, mathematical and graphical way of, you know, adding vectors together. And that's going to be, you know, basically a lifesaver if you really get this, you know, concept, you know, and understand it and be able to visually and analytically be able to calculate it.